Hello students, welcome to InstaOwl Science class where we believe in democratizing education for all. Now, let us continue with our topic in science, electricity. In the previous section, we discussed about electric current, understood the concept of potential difference and examined the verification of Ohm's law. And now, we will understand the concept of a series connection of resistors and how it affects current, voltage and resistance in a circuit. In a series circuit, resistors are connected end to end, allowing electric current to flow through a single continuous path. As a result, the current remains the same through all the resistors in the series. However, the total voltage supplied by the battery does not stay the same across each resistor. Instead, it is shared among the resistors in proportion to their resistance values. This means the total voltage across the series connection is equal to the sum of the voltages across each individual resistor. Mathematically, we can write this as V total equals V1 plus V2 plus V3. Now using Ohm's law, which states that voltage equals current multiplied by resistance, we can determine the voltage across each resistor. For the first resistor, the voltage V1 is equal to the current I multiplied by the resistance R1. Similarly, for the second resistor, V2 is equal to I times R2, and for the third resistor, V3 is equal to I times R3. Moving further, we substitute these expressions into our total voltage equation, which is V total equals V1 plus V2 plus V3. We get V total equals I times R1 plus I times R2 plus I times R3. Since the current I is the same in all three resistors, we can factor it out, giving us V total equals I times the sum of R1, R2 and R3. Now, from Ohm's law, the total voltage across the entire circuit can also be expressed as V total equals I times R total, where R total is the total resistance of the circuit. Comparing this with our earlier expression, we find that the total resistance in a series circuit is equal to the sum of the individual resistances. Therefore, R total equals R1 plus R2 plus R3. In summary, in a series connection of resistors, the same current flows through each resistor, the total voltage is divided across the resistors, and the total resistance is the sum of all individual resistances. Let us now proceed to understand the concept of the parallel connection of resistors and derive the expression for their total resistance. In a parallel circuit, multiple resistors are connected such that each has its own separate branch, but all branches share the same starting and ending points. This configuration ensures that all resistors are connected across the same 2 points. Because of this arrangement, the voltage across each resistor in a parallel connection is the same. That is, the voltage across the first resistor, the second and the third are all equal to the total voltage supplied by the source. We express this relationship as V equals to V1 equals to V2 equals to V3, where V is the total voltage and V1, V2 and V3 are the voltages across the individual resistors. On the other hand, the current behaves differently in a parallel circuit. The total current flowing from the source splits among the branches, with each branch carrying a portion of the current based on its resistance. Hence, the total current denoted by I total is the sum of the currents through each resistor. Mathematically, this is written as I total equals to I1 plus I2 plus I3. To find the current through each resistor, we use Ohm's law. For the first resistor, the current is I1 is equal to V upon R1. Similarly, I2 equals to V upon R2 and I3 equals to V upon R3. Substituting these values of I1, I2 and I3 into the total current equation, that is, I total is equal to I1 plus I2 plus I3, we get I total is equal to V upon R1 plus V upon R2 plus V upon R3. Factoring out V from this equation gives us I total is equal to V multiplied by 1 upon R1 plus 1 upon R2 plus 1 upon R3. From Ohm's law, we also know that the total current is related to the total resistance and voltage by the formula I is equal to V upon R total. Comparing this equation with the previous one, we can equate the expressions for I total giving us V upon R total, which is equal to V into 1 upon R1 plus 1 upon R2 plus 1 upon R3. Dividing both sides by V, we get 1 upon R total equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Thus, in a parallel connection of resistors, the reciprocal of the total resistance is equal to the sum of the reciprocals of the individual resistances. Let us perform an activity to experimentally verify how potential difference is distributed in a series circuit. We begin the setup by inserting a voltmeter across the ends of X and Y of a set of 3 resistors, R1, R2 and R3 connected in series. The voltmeter, which is always connected in parallel to the component across which the voltage is to be measured, gives us the total potential difference across the entire combination. We first plug in the key to close the circuit and record the voltmeter reading V across the points X and Y. This value represents the total voltage across the series combination. To ensure consistency, we also measure the potential difference directly across the battery and compare it with the value of V. Since there are no other components in the circuit aside from the resistors and measuring instruments, both readings should be equal, validating the initial setup. Next, we disconnect the voltmeter across X and Y and instead measure the potential difference across each individual resistor. We can start by measuring V1 across the first resistor R1, which lies between points X and P. Then, we measure V2 across the second resistor R2, placed between points Q and S. Finally, we measure V3 across the third resistor R3, positioned between points T and Y. Each voltmeter is again connected in parallel to the respective resistor during these measurements, as we can see in the diagram. After obtaining the values of V1, V2 and V3, we compare their sum with the total potential difference V, initially recorded across X and Y. It is observed that V1 plus V2 plus V3 is equal to V. This confirms that in a series combination of resistors, the total potential difference across the entire arrangement is equal to the sum of the individual potential differences across each resistor. This is mathematically expressed as V is equal to V1 plus V2 plus V3, and the experimental setup and data fully support this conclusion. Let us now proceed with the concept of the heating effect of electric current. This phenomenon can be easily understood through common examples from everyday life, such as an electric iron. When the electric iron is plugged in and switched on, an electric current flows through a resistive element inside the appliance. This element is specifically designed to offer resistance to the flow of current. As the electric current encounters this resistance, it produces heat, a direct consequence of the heating effect of electric current. The heat generated is transferred to the base plate of the iron, enabling it to remove wrinkles from clothes. Another familiar example is that of an electric bulb. Within the bulb, an electric current passes through a thin filament. The resistance of this filament causes it to heat up to such a high temperature that it begins to glow, emitting visible light. This glowing filament is a clear demonstration of the heating effect being used to produce light. This principle is also observed in other appliances such as electric toasters and kettles. In a toaster, the heating coils glow red as they convert electrical energy into heat, toasting the bread. In an electric kettle, the heating element rapidly raises the temperature of water. Even the warmth you feel from a mobile charger during use is due to the same effect. The conversion of electrical energy into heat because of resistance in the internal components. These examples clearly illustrate how the heating effect of electric current is applied in various practical situations where electrical energy is converted into heat to perform useful work. Now that we've understood how electric current produces heat in appliances, let's look at where this energy comes from and how it behaves in different circuits. The source of electrical energy in a circuit is typically a cell or battery. When connected, it generates a potential difference which causes electrons to move through the circuit, particularly through the resistors. This movement of electrons allows electrical energy to be transferred and used for various purposes, either to perform mechanical work as seen in electric fans or to produce heat as in the case of electric heaters and irons. Next, in a purely resistive circuit, such as those found in devices like electric heaters and irons, all the supplied electrical energy is converted entirely into heat. This dissipation of energy as heat is a direct result of the resistance offered by the circuit elements, and it forms the basis for the functioning of many heating appliances. Most electrical devices operate by using this principle of converting electrical energy into useful forms of energy, whether mechanical or thermal. Let us now take a closer look at how a purely resistive electric circuit functions. This basic yet informative setup illustrates the role of each circuit component and how they work together to demonstrate the heating effect of electric current. In the given diagram, the central element is a resistor, that is R, which resists the flow of electric current and converts electrical energy into heat. This resistor is connected in series with the rest of the components in the circuit. On the left side, a cell or battery acts as the source of electrical energy by creating a potential difference, which drives the flow of electrons through the circuit. Just below the battery is a key, K, which serves as a switch. When the key is closed, the circuit is complete and current begins to flow. When the key is open, the circuit is broken and no current flows. To the right, an ammeter denoted by A is connected in series with the resistor. The ammeter measures the electric current flowing through the circuit. Across the resistor, a voltmeter V is connected in parallel. Its function is to measure the potential difference across the resistor. When the key is closed, the battery drives a current through the circuit. The resistor opposes this flow, converting part of the electrical energy into heat. The ammeter provides the current reading, while the voltmeter displays the voltage drop across the resistor. Together, this setup effectively demonstrates the heating effect of electric current in a purely resistive circuit. Let us now understand the concept of Joule's law of heating, which explains how electric current produces heat in a conductor. According to this law, the heat generated in a resistor is directly proportional to three factors: the square of the current flowing through the resistor, the resistance of the conductor, and the time for which the current flows. This relationship can be expressed mathematically as H equals I squared multiplied by R multiplied by T, where H is the heat produced in joules, I is the current in amperes, R is the resistance in ohms, and T is the time in seconds. This indicates that as the current increases, the heat produced increases quadratically, since it is proportional to the square of the current. Similarly, if the resistance of the conductor increases while the current remains constant, more heat is generated. Further, the longer the current flows through the resistor, the greater the amount of heat produced. Each of these factors contributes independently to the total heat, and together they define the heating effect quantitatively. To relate this to the broader concepts of electric work and power, consider what happens when a charge moves through a potential difference. In doing so, work is done by the electric field. The work done, denoted by W, is directly proportional to voltage and charge, and as such it is defined as the product of the potential difference and the amount of charge moved, or W is equal to V into Q, where V is the potential difference in volts and Q is the charge in coulombs. Now, moving on to understanding electrical power in a circuit, we begin with the definition of power as the rate at which work is done or energy is transferred. In the context of an electric circuit, electric power refers specifically to the rate at which electrical energy is converted into other forms of energy such as heat, light, or mechanical energy. The basic formula to calculate electrical power is given by the expression power equals voltage multiplied by current. Mathematically, this is written as P is equal to V into I, where P is the power in watts, V is the potential difference in volts, and I is the current in amperes. The SI unit of power is watt, denoted by capital W. 1 watt is defined as the power consumed when 1 ampere of current flows through a potential difference of 1 volt. That is, 1 watt is equal to 1 volt into 1 ampere. Additionally, 1 kilowatt is equal to 1000 watts. We can derive the alternate forms of the power formula using Ohm's law, which states that V is equal to I into R, where R is the resistance in ohms. Substituting this into the original formula, P is equal to V into I, gives us two other useful expressions. If we replace voltage in terms of current and resistance, we obtain P is equal to I square into R, which is used when current and resistance are known. Alternatively, expressing current as V divided by R and substituting into the formula gives P is equal to V square divided by R. It is useful when voltage and resistance are known. These different forms of the power formula allow us to calculate power depending on the known quantities in a circuit. The relation between power and heat produced in a resistive circuit is also significant. The heat generated in a resistor over a certain time is given by the product of power and time. Thus, Heat, that is H, is equal to P into T. Using the formula for power as P equals to I square into R, we substitute and obtain the expression H is equal to I square into R into T. This is known as the Joule's law of heating, and it quantifies the heat produced due to the passage of electric current through a resistive conductor over a time duration T. This set of relations helps us understand how electrical energy is used and converted within a circuit. Now, let's take a practical example. An electric heater with a resistance of 10 ohms and a current of 2 ampere flowing in it for 5 minutes, how much heat will it produce? In this case, the resistance R is given as 10 ohms. The current I is 2 amperes and the time T is 5 minutes. Since time must be expressed in seconds for the calculation, we convert 5 minutes to seconds by multiplying 5 by 60, giving us 300 seconds. Let us now solve this example step by step using Joule's law of heating. According to the law, the heat produced in a resistor is equal to the square of the current multiplied by the resistance and time for which the current flows. Substituting these values into the formula, H equals I squared times R times T, we get H equals to 2 squared into 10 into 300. This simplifies to H equals to 4 into 10 into 300, which gives us a result of 12,000 joules. Therefore, the heat produced by the electric heater in this duration is 12,000 joules, which is equal to 12 kilojoules. Let's now turn our attention to how electrical energy is measured, especially in practical terms such as household consumption. The standard unit used to measure energy consumption in our homes is the kilowatt hour, abbreviated as kWh. This unit is what you typically see on electricity bills, where it reflects the total amount of electrical energy consumed by all devices in a home over a certain period. To understand this better, let's define what 1 kilowatt hour means. 1 kilowatt hour is the amount of electrical energy consumed by an appliance with a power rating of 1 kilowatt, that is 1000 watts, when it operates for 1 hour. This definition helps us relate power and time directly to energy. Mathematically, we can express this as 1 kilowatt hour equals 1 kilowatt multiplied by 1 hour, which is equal to 1000 watts multiplied by 3600 seconds. This gives us a result of 3.6 into 10 raised to 6 joules. Now, let us understand energy consumption with a simple real-life example. If a 100-watt bulb runs for 10 hours, the energy consumed is calculated by multiplying power with time. So, 100 watts multiplied by 10 hours gives us 1000 watt-hours, which equals to 1 kilowatt hour. This means one commercial unit of electricity is used, as seen in household electricity bills. Moving on, the heating effect of electric current finds several practical applications in everyday electrical appliances. One of the most familiar examples is the electric bulb. The filament inside the bulb emits light as a result of the heating effect of current. This filament is typically made of tungsten, a material chosen for its high melting point of approximately 3380 degrees Celsius, which allows it to withstand extreme temperatures without melting. As electric current passes through the filament, it heats up to the point where it begins to emit visible light, thus converting electrical energy into both heat and light energy. Another common application is the electric iron, where the heating element is made from alloys that possess high melting points. These alloys are selected specifically to ensure that the element can heat effectively without being damaged. Electric irons, heaters and geysers all function on the same basic principle. They convert electrical energy into heat to perform specific tasks such as pressing clothes, warming spaces, or heating water. The electric fuse is yet another crucial application of the heating effect. It serves as a safety device designed to protect electrical appliances from high voltage or overcurrent situations. A fuse is composed of a thin wire made of metals or alloys like aluminium, copper, iron, or lead. When excessive current flows through the circuit due to a fault or overload, the fuse wire heats up rapidly and melts. This melting action breaks the circuit and stops the flow of current, effectively protecting the connected appliances from damage. Thus, the fuse operates based on the same heating principle, using it as a safeguard in electrical systems. Now, let's uncover some interesting facts with our Instabytes. Did you know electrons are not consumed in an electric circuit? What we pay for is the energy required to move these electrons through appliances like bulbs, fans, and engines, not the electrons themselves. In electric heaters, the heating element is made of an alloy with very high resistance, which heats up and glows red due to the heating effect of current. Meanwhile, the connecting cord, made of low resistance materials like copper or aluminium, remains cool. Similarly, the coils in electric toasters and irons are made of alloys instead of pure metals, as alloys have higher resistivity and do not melt easily at high temperatures, ensuring both safety and efficiency in high heat applications. And now, it's time to recap what we have learned in this video using our Instalights. We started with series connection, where resistors are connected end to end and the total resistance is the sum of individual resistances. Then we moved on to parallel connection, where resistors are connected across the same 2 points and the total resistance is reduced. We then discussed electric energy, which refers to the work done to maintain the flow of current. And finally, we looked at electric power, which is the rate at which electrical energy is consumed or transferred in a circuit. With that, we conclude today's session. Keep learning with our Insta Owls videos. See you in the next one. Goodbye.